Good? Or close? Okay, I see a few people going. I'll let you finish. I'll just start talking a little bit here. So you've been doing this formula actually for a long time. When we were looking at geometric functions, this is kind of like the base of that. Okay, but it would be going to term 0, not to term 1. And it's kind of nice it doesn't go to term 1, it goes to 0, because then when we're looking at years, it's easier to do a quick calculation. Or there's less thinking, I should say. So we are going to use this only when you are looking at interest that is simple interest, so it's in the problem on this one, or if the interest is only calculated once per year. If it says compounded and it gives you any other number than 1, then we use a different formula. Looking at this, I can identify a few pieces. So this 5,000 is going to be my principal. That's my starting amount. The interest rate is at 13%. For the 13%, whenever we're using a rate, we always need to convert it to a decimal. So really quickly, if you got a percent symbol, you just divide that number by 100 if you're stuck on it. And in this case, we get 0.13, so that would be our rate. And then we're looking at how long are we actually looking at doing this, and that would be for 3 years. So let's just fill out our formula quick. I'm going to have A of 3 is equal to 5,000. Then I got 1 plus 0.13 to the third power. Now I don't need you to write it like that. I'd be actually okay if instead you wrote it like this. And once you write it like this, you can actually type that whole dang thing in your calculator and you can get an answer. So let's go ahead and type it in and make sure we all get the same thing. Like I said, this is a very heavy calculator portion, which is a switch from this unit because we used to always say get those calculators away. And now I'm telling you to get those calculators out. I'm writing part of the number up there, but not the whole number. I want you to give me the rest of the number. So 7,214 point what? It is 49. We are going to round up because that 5 is telling us we have to round up. Oh, yes, they would on this. Yep, they would. Because you're paying them. Correct. So we got this. So think about that really quickly. 3 years, they gave you $5,000. 3 years later, you have now paid them $7,214.49. You paid them in 3 years just over $2,000. Just for using their money. 13% is actually pretty typical for a personal loan right now, which is something you would be looking at if you're doing a snowmobile. They might give you a slightly better rate, but it's not going to be a whole lot. So it's kind of just food for thought for you. Think about how debt impacts you. Think about how savings impact you. Next problem. This is the new piece. So number of times interest is compounded in a year. Everything else is the same. You don't have to write what's in the upper right corner. Just write the words down. wrote some stuff in the upper right hand corner because that's just to show you I could use this formula for basically this case and for the previous case. Because the simple interest formula is just a simplified formula of the compound interest. So when I look at this, if I'm only calculating my interest rate once per year, that means n is going to be 1. So what's r divided by 1? What's t times 1? It's just r and t. So it is the same formula, it's just a simplified form. Because of that, you don't have to remember both of them. You're going to be given these formulas, but when in doubt, choose this formula and just plug in the pieces you need to know. Now, we got some information here. It looks like we got a savings account that was set up for us by our 65-year-old self from the future, because we did travel to the future and came back and made sure everything worked out. And that account starts with $35,000 in it. Now, this is for our retirement, and so we found an account that pays 8% interest compounded monthly. This piece right here, compounded monthly, that's telling me which formula to use. That's telling me to use this compound interest formula because n is now a number. Last thing we have to do, we have to look at how much time has passed, 47 years. So we now know all the pieces of information, we just have to enter them into the problem. First things first is your principal. And so I'm going to say A of 47 because that's how many years I'm looking at. T is the same regardless of where it's at. So I'm going to have 35,000. Then in parentheses, I'm going to have 1 plus, what is 8% as a decimal?
0.08.
0.08. And how many months are in a year? 12. So that means I'm going to do 0.08, which is R. This is P. And I'm going to divide it by 12. So that's N. And then up top, I'm going to have N times T, which is going to be 12 times 47. Now, before you grab those calculators, this is how I would type it in. I would start by only typing in what's inside the parentheses here. And by doing so, you don't need any parentheses. So I'm just going to type in 1 plus 0.08 divided by 12, and I'm going to hit enter. So let's all do that. You might have to wait it just a little bit so everybody's on the same page. But we type just that little thing and we hit enter and we get 1.00666. How many ways is it a 7? Hit enter. All right, so we got that. Next thing I do is I go ahead and I hit the caret button. And I go ahead and when I do that, I have to put parentheses and I have to put 12 times 47. Close the parentheses. What that's doing is it's just following order of operations. I did what's on the inside of the parentheses. I'm now raising it to the 12 times 47, that power. What happens if I don't do parentheses? It goes to the 12th power, but then it multiplies it by 47. That's not what we want. So you got to parentheses that. You hit enter. It gives me 42.415 something, 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 something. By not clearing this, I'm not rounding anything. And then the last thing we do is we just go times 35,000. And so, future self did a good job. His future self saved 1.5 roughly $1 million for us. Anybody not getting this number? Because I want to make sure you get this number right now. All right. Just start with 1 plus 0.08 divided by 12. Enter. Exponent key. And then parentheses, and then 12 times 47. And then times 35,000. Anyone else? Seven, enter. And all right, anybody else? Next, look at that. Continuously. Every single moment, instantaneously. It's always happening. If that is the case, we use this formula. Now, what letter is new? E. But what letter is here? There is no E. That's because E is a number. So E is approximately 2.71, and then it just goes. And I'm not going to put dots there actually because it's like pi. It keeps going on and on and on, and it just keeps going. And so we use this in a lot of financial problems, and we also use it with population. And I'll talk more about the population when we get there. But how do I know I use this formula? I know because of this statement right here. If I see that, I'm using this formula. So really I have two formulas right now. I have compounded interest when there is a specific number, like 1 year, 12 times out of the year, things like that. And then I also have the compounded continuous formula. So let's start filling out pieces we know. P is our starting amount. In this case, we have parents that deposited $12,000 into an account for your college fund. So that means our principal is $12,000. We also know this is going to be for your 18th birthday. So we're looking at 18 years when we do this problem. So I'm going to have A of 18 is equal to my principal, which is 12,000. Then I go ahead and I put E. And then we got RT. Now T is 18, but what is R?
9.3.
0.093. So we're going way over. So 0.093. And then times 18. Now let's talk about this in one other way really quick. So this is continuous. It's always happening. So how do you remember to use E? Well, I'm going to draw something here. So that's E. But then I'm going to draw bad. I'm going to draw really messy. What does that make? It makes a circle. Circles go forever. Really bad analogy, but it's something. Okay, there's something there. So E means it's compounded continuously. Now we got to type this in. But where the heck is E on your calculator? Find the key ln. You don't hit ln. You have to hit second and then ln. And ln is just 2 down. There's a difference. I'll come and help you out. Or do you find it already? Now, you can absolutely type in E to the 0.093, and it's nice because it actually puts a parenthesis up there for you. And then times 18 and get a number, and then times that by 35,000. Or 12,000, sorry. I wouldn't actually do that. I would start with 12,000. Then I would hit second, ln. I'd get the E. And then since the parentheses there, I go 0.093 times 18, close it, and boom, I got my answer. This one's easy to type in all in one line because of how E is set up in your calculator. This is one of the times where your calculator actually helps you out instead of hurts you. You find E on yours? Okay. So in this case, we get A sub 18, or of 18 is equal to, looks like $64,001 and 51 cents. questions? Again, come back to the beginning of the problem. What are we looking for? How many times are we compounding this thing? In this case, it's continuously. That's why we're using this formula. That's how it goes. That's what you have to look for. Moving. What do you think all those things are? What do you think n of t is? What was a of t?
Out after a year.
Not necessarily 1 year, but after a certain amount of time, right? It's your final amount. It's still your final amount. You don't have to write it down. You can write it down if you want. This formula, n sub o, the initial population. So it's just dealing with population, but they're the same exact formula, just different letters. We switch those letters so it's more representative of population. So it cues your brain that you're talking about creatures or humans or something else instead of money, because all the other problems deal with money. So, a couple things with population. Whenever we do population in class, we are going to use E. We're going to use this formula right here, or you can say it's the other one, the first. Now, we are using E, not because it is the only multiplier for a population, but because it's very common to do so. So in other classes, you might get something else, and that's fine. In this class, we're only going to focus on using E for populations because we're looking at a population as they're growing continuously. So it's always changing. It is always in motion, and that's why we use this. Okay. Again, it is not the only multiplier, but it is the one that we are going to use for every single population problem in here. Now, we're looking at some stuff here. I want you to identify for me my initial population, my rate, and how much time is passing. What is our initial population? Yeah, it's that 510,000, blah, 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 blah. Okay, 704. Now, our rate, what's our rate?
0.23.
Give it one more zero in there, 0.023. Okay, you can always double check your numbers. Remember, you can take 2.3 and divide it by 100 and get that. Time, how much time has passed between 2026 and 2039? Oh, in 2024. Yeah, my bad. I was looking at that first one. Thank you. 15? Yeah. So we're looking at 15 years. So let's just fill everything out. Maybe if this, there we go. Do we like that answer? Why not? You do. I don't know if I really like that answer. Should we have decimals? No, because we're talking about people. You get something else to do?
I got 721.09.
Because you rounded up, right? We are going to round in here just to the nearest person or animal or whatever. So that would be good. Okay. So we would put 9 there based off that. So today, that's what we're going to just do. We're just going to round to the nearest person or whatever we're talking about, and we're going to call it good. Now, there's other roundings that you could get into, but we will leave that for a different class. Example 2. This one's kind of weird for you. So let's think about what this formula is saying to do. So we're looking at Chicago, and it has this population right here, about 2.7 million in the year 2020. The population is currently declining and kind of hinting at what in your brain? Negative. Okay. So declining is going down, so at a rate of 0.3%. So again, we're looking at population. We are looking at something that is continuously happening. It's always changing. We are going to use E for that. So I'm going to start with my current population, which is the roughly 2.7 million. I'm going to go times E. What is my rate?
0.7.
No. So remember in your simple interest formula, we had 1 plus or minus R. So we would subtract if we were taking away, but we don't have a 1 this time, and that's weird for a lot of people. So instead, I'm actually going to just have minus or a negative 0.003. We'll talk about why that works in just a moment. How many years have passed? 30. So think about this. This is going to give me a negative exponent, right? What do negative exponents give you? They become positive by being flipped. So by doing that, we actually make this a fraction. We make it 1 over a number, and that is going to give us exponential decay. So it's a tricky way of doing that, but that's what's going on. So let's type that in, get a number, round according to the nearest whole person. Would that be the nearest person? What would be the nearest person? 10. Yeah, we'd actually round up 1. So if we're rounding to the nearest person, that's what we're looking at. Let's think about that answer. Does it seem appropriate? Does it seem logical? Does it seem like it could be possible? Yeah, we're losing, but we're losing only 0.3%. We're losing such a tiny amount. So over 30 years, we're really not going to lose a ton, right? Our population is going to be somewhat stable, but we are dropping about 200 some thousand people. So it does seem reasonable over 30 years. Please think about that, because I've had answers of negative like 1,300. You have negative 1,300 people? No, you get to 0 and you're kind of done. Like it doesn't change after that. Unless maybe they're talking about zombies, I don't know how that works. So regardless, please just be cautious about that. Any questions about what we did today? Last thing that we are going to do is talk very basically about logs. I do not want, you don't have to write anything down. If you want to, you can write it on your last piece of paper. Now, when we graph logs, we focus on these two items right here. So we just have to get really good at doing those two items, and if we can do that, we can graph very easily. So we are just going to talk about a few things really quick, and then you're going to have the rest of class for work time. So if I give you a crazy log like this, log base 99 with an argument of x, and I'm going to graph that. I'm not going to probably graph that because it won't work very well. But if I'm filling out my table, what am I going to plug in for x? What numbers am I going to use? I only need two. What two numbers? 1 and 99. So I'm playing like a matching game, right? I'm just getting 1 and 99. And that gives me those two items, so I could solve those really quick and get 1 and 0. Easy peasy. If we change the premise of the game, and let's say I did log of 23, what numbers am I still going to use? I'm going to use 1 and 23, so I'm pretty much always using 1, so I get 1 and 23. So if you get a basic log, it should be really quick. What happens when you don't get a basic log? So I'm going to give you something different. So what if I give you log and I give you 99 again, but I put x plus 1? Let's think about this really quickly. On a graph, your log looks like this. Okay, it looks something like this. What is my asymptote if I have x plus 1 in there? -1. So if you have an asymptote of, or if you have this log right here, your asymptote is -1. So that means your graph is being pulled to the left. That means your x coordinates are now pulled to the left. So what numbers am I going to plug in here now? I want to get 1. I want to get 99, right? If I plug those in and I get them in here, I got my answer very easily. So what do I have to plug in for x so that I get 1? I plug in 0 now, which makes sense because I shifted to the left 1, and I shifted this to the left 1. So this would be 0. What is, instead of 99, I'm now putting in what? 98. Because again, I've shifted to the left 1. That is what we're looking at. Now we're going to change the premise a little bit more, and I'm going to do one other thing. Again, I am only looking for the 2 points that I need to graph. If I have log of 70 times, I got 99 out front here, and then I get x plus 10. If I'm looking for my 2 points, sorry, I lost my train of thought. Does the 99 matter? Not right now. It matters when I calculate what the number is for y. But right now, it doesn't matter what I'm choosing. So we need to look at the problem and think about what do I actually need to start this problem. You go step by step. So I don't need this for the moment because I'm not doing anything with it. What number am I going to plug in for x so that I can get a 1 in there? -9, and that makes sense because if you think about this, our asymptote would be at -10. So we shifted all of our points in that direction. Now, what is my other point that I'm going to plug in? 60, because if I go 60 plus 10, I get 70, which gives me back to this. Now I can get my answers. So honestly, when I plug in -9, I get a 1 right there. I get 0. 0 times 99 is still 0. If I plug in the 60, that's when the 99 is doing something. Now I get 1 times 99. Now I get 99. We're getting a stretch. We're getting growth that we didn't have before. Questions? Hopefully that helped you out a little bit. If you were struggling with logs. Tomorrow we got whiteboard practice. Then we got your formative quiz. Your quiz is going to be a little bit longer than it has in the past, but it's also going to be less quiz-like. And then we got review. In your homework packet, you have a review assignment. We are giving you that whole hour to get that review assignment done, and then test on Friday. Now, think about what's on your test. Exponent properties, first lesson. Okay, you're going to have a couple of those. You're going to have a graph of an exponential function, a graph of a log function, and then you're going to have problems like these. I've had people finish this test in about 3 minutes. Very well. It's a short test if you know what you're doing. If you don't, it might take a little bit longer, and that's fine. I don't expect you to do the test in 3 minutes, nor do I want you to, because I want you to double check things and make sense of your work. But I'm telling you that because this could be a slam dunk for you, and that would really benefit your grade, right? Short unit, short test, get the material down really well, score really good, move on to the next chapter. The next chapter is more logs. They don't go away. So we might as well learn them now, so then we can do better with them later on. The time is yours to work.